Gonna be solving Cambridge International AS and A Levels Chemistry Paper 1 Multiple Choice May June 2025 Paper 11. So let's get going. We're gonna start this paper from the last question and then we're gonna go up. Okay, because I guess organic is like a little more trickier. That's why we're gonna start with the last question. So here we go. Hydrocarbon X is saturated. Saturated means that it's going to have only carbon-carbon single bonds. Each molecule contains one ring of carbon atoms. Okay, so we're dealing with compounds that have rings. So maybe it's a 5 ring, a 2 ring, a 3 ring, a 4 ring. I don't know what kind of ring it is, but it's a ring. Okay. The mass spectrum of hydrocarbon X is measured. So we're doing mass spectrometry. The peak representing the M plus ion is 14 millimeter high. The peak representing the M plus 1 plus ion is 0.77 millimeter high. What is the mass to charge value of the M plus ion of X? Okay. So I've basically drawn this mass spectrometry like spectrum to show you guys what's basically happening. You know that the M plus peak is because of the carbon 12 atom and the M plus 1 peak is basically because of carbon 13, and the ratio for this is like 99 and then 1.1% in that thing, whatever that thing is. And then the formula we use for the number of carbon atom is that 100 upon 1.1 multiplied by the ratio of M plus 1, which over here was coming out to be 0.77, upon the ratio of M plus 2, only the M peak, which was coming out to be 14 millimeters. I used the formula, got 5 number of carbon atoms. Now I know that I'm going to have 5 number of carbon atoms in this saturated hydrocarbon, and they also told me that it contains one ring. So I have to make a ring with 5 carbon atoms. So that's going to be a pentagon because it contains 5 carbon atoms. I just calculated, and now what do we have to calculate? We basically have to calculate the mass to charge ratio of the M plus 1 peak. That's the molecular mass. So if we add 5 carbons, carbon, 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 and we know that since it's a ring, so each carbon is going to have 2 hydrogens attached with something like this. Now for 5 carbon atoms, the mass is going to be 5 times 12 because for 1 carbon it's 12 plus 10 for the number of hydrogens. You can count, we have 10 hydrogens. That's going to be 60 plus 10 equals to 70 over here. So the answer is going to be 70. That's going to be the mass of the the mass to charge ratio of the M plus peak. And now if they're asking about the M plus 1, then you can simply tell it's going to be 71, just one more than 70. This was easy. The structural formula of hept 145 triene is shown. How many of the carbon atoms in one molecule of hept 145 triene are sp2 hybridized? So now over here, you have to draw the structure in order to realize what's going on to calculate the hybridizations. So let's start with drawing the structure. So over here we have a carbon that's double bonded to 2 hydrogens. Not double bonded, single. Then we have a double bond over here. You got to draw the double bonds because if you don't know the bonding, how can you figure out the hybridization? Well, a hydrogen here bonded to a carbon, hydrogen. I'm just opening this up because if I don't open it, I'm gonna be damn honest, I cannot even tell without opening that. C. Okay, CH I've drawn. Then there is a C double bonded to another C, H, and then there is C, H, H, and H. If you don't open it, I don't think anyone can tell without opening it. How many of the carbon atoms in one molecule of hept 145 triene are sp2 hybridized? So now we got to look at sp2 hybridization. So to know the hybridization, first let's see what's going to be the hybridization starting from this carbon atom. This carbon atom is making 2 single bonds in 1 double bond. So this is going to be sp2 hybridized. Why? Because we have a trigonal planar geometry. You can see the bond angle is 120 degree and the carbon is making 3 bonds. So this carbon is sp2 hybridized. Then this carbon over here again is making 2 single bonds, 1 double bond, trigonal planar geometry. This carbon is also going to be sp2 hybridized. Then we come to this carbon. This carbon is making 4 single bonds, 4 sigma bonds. So it's going to be sp3 sp3 hybridized. That's a tetrahedral geometry. So this carbon is sp3 hybridized. Now coming on to this carbon, it's making two single bonds, two sigma bonds in one double bond. Like this one's a pi bond and this one's a sigma bond. So again, trigonal planar geometry, and this is going to be sp2 hybridized. Now coming to this carbon atom is making two double bonds. So this is not going to be sp2, this is going to be sp hybridized. How do I know? Because the formula for hybridization is simple. If you don't get it for this carbon, just use the formula. The formula says, according to the formula, it's number of attached atoms plus the number of lone pairs. That's the amount of orbitals that are going to be involved. So how many carbon atoms or different atoms are attached to this carbon? One atom and two atom. So the number of attached atom is 2 plus how many lone pairs do we have? We have a 0 lone pair for this carbon. So plus 0 equals 2. That means two orbitals are going to be involved in hybridization. One is going to be an s orbital, the other one's going to be a p orbital. So this carbon atom is sp hybridized. Then talking about this carbon atom, two single bonds, one double bond. Again, we know this is going to be sp2 hybridized. And then this carbon atom making four single bonds is sp3 hybridized. So that's how we're going to look at the hybridization. Now, how many sp2? 1, 2, 3, 4. 4 carbon atoms that are sp2 hybridized. Okay. Might seem tricky, might seem challenging to some, but you just have to realize what's going on inside the structure. That's why I just thought, why not begin from this is S and this is sp3 hybridized. Okay. Next question. The structure of the testosterone molecule is shown. Okay, so that's a hormone, and we have the structure of it. Which statements are correct? Carbon atoms C1 and C2 can be oxidized with acidified K2Cr2O7. So carbon atom C1, which is over here, can this be acidified? Let's look what's over here. So we simply have a carbon that's attached to another carbon on top, another carbon 2 on the bottom, and then we have a double bonded O. What kind of functional group can you see over here? This is a ketone functional group, right? So over here, we are dealing with a ketone functional group. So this one over here is a ketone, right? When we're dealing with ketones, we know that ketones cannot be further oxidized. Carboxylic acids cannot be further oxidized. Ketones cannot be further oxidized. Aldehydes can be oxidized. Aldehydes can be oxidized to form carboxylic acids, but ketones cannot be oxidized. So C1 cannot be further oxidized. So we're going to write not oxidized by K2Cr2O7. Next, we have this carbon atom that's attached to a carbon here, a carbon here. So over here, we see that this is and one hydrogen as well, right? One hydrogen. So we can see that this is what kind of alcohol is this? This is a secondary alcohol because it's attached to two R groups in one H. So that's a secondary alcohol. And what do you think? Are secondary alcohols oxidized or not? Yeah, they are oxidized. So this can be oxidized to form a ketone. Secondary alcohols oxidized to ketone, primary alcohols oxidized to form aldehydes or carboxylic acids. So carbon atoms C1 and C2 can be oxidized. No, only C2 can be oxidized, not C1. There are fewer than 27 hydrogen atoms in one molecule of testosterone. So there are fewer than 27 hydrogen atoms. Fewer than, that means less than. So we got to calculate or count the number of hydrogen atoms. If some way I can bypass this thing, no, I cannot. Even if my third one is correct, let's see if third one is correct or not. Because this is a long task, which I want to avoid. That's why I'm going to go with option 3 first. There might be some way I can just bypass this. There's 6 chiral carbon atoms in one molecule of testosterone. So now we got to calculate the number of chiral carbon atoms. This is a chiral carbon. Let me use a different color. This is a chiral carbon. This is a chiral carbon. This is a chiral carbon. Chiral. 1, 2, 3, 4, 5, 6. Yeah, the exactly 6 chiral carbon atoms. So this one's correct. So now, if this one's correct, then I have to check option 2 as well. There are fewer than 27 hydrogen atoms. Okay, now I have to calculate the hydrogen atoms. Okay, it's fine. No worries. This carbon, there are going to be 2 hydrogens. For this carbon, there are going to be 1 hydrogen. For this carbon, no hydrogen. 2 again. No hydrogens. 3 are already there. 1, 2, 3, 4. 1, 2, 1, 2, 1, 1, 1, 2, 1, 2. So I counted all the number of hydrogen atoms. It took a while. I was missing some. Like now, my total count is 28. 28 is the total number of hydrogen atoms I have got according to my count. Okay, so now they're fewer than 27. No, they're not fewer than 27. They're more than 27. They're 28 hydrogen atoms according to what I've counted. So according to that, only option 3 makes sense. So this is going to be the answer. Next, 3 substances are listed: butane, hydrogen, and hydrogen bromide. Which substances are possible products of the free radical substitution reaction between ethane and bromine? Okay, so free radical substitution between ethane and bromine. So let's do the free radical substitution. Ethane means carbon, carbon, hydrogen, 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 and hydrogen. That's ethane molecule, right? Ethane. And now the bromine molecule is Br and Br. Firstly, we know that this bond is going to break because of the sunlight, because of the activation energy we're going to provide it. And then we know this bromine can come here or here or here. Okay, and that's how the free radical substitution reaction is going to propagate. Over here, now we know that we can form a C2H5, 1, 2, 3, 4, 5. One bond is going to be breaking, C2H5 free radical. And then we know we can form a C2H5 free radical. So these 2 free radicals can react to form C4H10. Okay, this free radical, which can be formed during the free radical substitution, can form, and this free radical can form. And then both of them can react to form C4H10, which is butane. Now, talking about hydrogen, we don't form H plus radicals, right? We don't form, because as they're formed initially. But then what do? We make them react with chlorine or bromine, and we form HBr or Cl. So over here, in case hydrogen bromide is going to be formed. Which substances are possible products of the free radical substitution? I guess 1 and 3. 1 and 3 only. Am I correct? Yeah, I'm correct. That's how it works. Okay. An alkene P reacts with an excess of hot concentrated acidified KMnO4. Methyl propanoic acid is the only organic product. What is alkene P? Okay. First things first. What do we gotta do? We gotta add excess hot concentrated acidified KMnO4 to this and then see what is the product. So 2,5-dimethyl-hex-3-ene. Hex-3-ene means 6 carbons. 1, 2, 3, 4, 5, and 6. And then 3-ene. 1, 2, 3 on the third carbon. I have ene part. And then 2,5-dimethyl. 1, 2-methyl. 3, 4, 5. Okay, done. Now, what do? I just add the hydrogens, H3, H over here, H over here, H over here, and H3, okay? Now, what do? I break it, because when I'm going to add acidified KMnO4, what's going to happen? The alkene is going to break, right? So, next step, break it from the middle, something like this. What am I going to form? On this side, this carbon is attached to 1 hydrogen and 1 alkyl group. When your carbon is attached to one hydrogen and one alkyl group, you form a carboxylic acid. You form a carboxylic acid, something like this. So I'm going to form a carboxylic acid over here. What kind of carboxylic acid I'm going to form? Let me see. H3C, C, CH3, H, and then C, double bond O, OH. That's the acid I'm going to form. And what do I call it? 2-methyl 1,2,3 propanoic acid. 2-methyl propanoic acid is what I'm going to form. Methyl propanoic acid. 2-methyl propanoic acid and methyl propanoic acid are the same thing. Why? Because you know that if you attach a methyl group to this carbon, which is carbon 1, which you cannot attach, so you cannot make 1-methyl propanoic acid, and if you attached it to this carbon, what's going to happen? You cannot have a branch at the terminal end. So even if you don't write 2, that's going to work out. So option A is giving me methyl propanoic acid. So I'm going to circle option A. But because I know that I'm sitting in exam, I know I have a little bit time, I'm going to check other options as well. Okay? 2-methyl butene. So 2-methyl butene. No worries. No worries at all. What are we going to do? Copy this stuff and draw everything. Copy and delete. Okay, we're gonna draw everything. Don't worry. Next is 2-methyl butene. So option number B I'm testing. Butene. 1, 2, 3, and 4. 4 carbon atoms. On the second carbon atom, I have a methyl, and then it's butene. So on the second carbon atom, I have this as well. Then if I complete it, it's something like this. And now it's time to break it. I'm going to break it from the center, something like this. And what do I form? Since this carbon is attached to one hydrogen and one methyl group, what I'm going to form? What am I going to form? Simple. Simple. Carbon attached to CH3, double bond O, OH. Only this part I'm counting. This carbon is going to get a double bond in OH. So what is this? I have formed ethanoic acid. Okay, what I formed? Ethanoic acid. Now I'm going to do with option number C. Okay, I have methyl propene. Propene means 1, 2, 3, and methyl means a CH3. So that is methyl propene. And now if I break this double bond, this carbon right here is attached to hydrogens only. So it's going to form carbon dioxide plus water. Okay, and this carbon over here is attached to 2 methyl groups. When a carbon is attached to 2 methyl group, what does it form? It forms a ketone. So it's going to form a ketone. So we're going to form carbon dioxide, water, and propanone. That is propanone. Okay, now let's do option C. Oct-4-ene C8H16. Okay. Oct-4-ene. Oct-4-ene means 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. 4-ene means on the fourth carbon I have double bond. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. I have a double bond on the fourth carbon, oct-4-ene. And if I break it from the middle, what I'm going to form? You can see it for yourself. If I draw the hydrogens, only for this, then CH2, CH2, CH3, CH3, CH2, CH2. You can see this carbon has one hydrogen and one methyl group. When you have one hydrogen and one methyl group, what do you form? You form a carboxylic acid. So over here, we are going to form a carboxylic acid, which is going to be CH3, CH2, CH2, C double bonded O, OH. And we form our 1, 2, 3, 4 carbons butanoic acid. And on this part as well, it's symmetrical. So we're going to form butanoic acid. So I've shown you that for option number B, we're forming ethanoic acid. For option number C, we're forming propanone, carbon dioxide, and water. For option number for option number D, we're forming butanoic acid. And for option number A, we are forming methyl propanoic acid. So our answer is going to be option number A. Two reactions are described. 2-bromo-2-methyl-butane. 2-bromo-2-methyl-butane heated with NaOH aqueous. 2-chloro-2-methyl-butane heated with NaOH aqueous. Okay, so when we're going to heat them with NaOH, what's going to happen is that a substitution reaction is going to take place, which is going to be a nucleophilic substitution. One nucleophile is going to replace another nucleophile. This OH is going to replace this bromine. This OH is going to replace this chlorine. And what are we going to form? Well, what we're going to form is an alcohol. Okay. In both reactions, the conditions are the same and NaOH is in excess. Okay. 30.18 grams of 2-bromo-2-methylbutane forms 12.32 grams of X. MR is given of 2-bromo-2-methylbutane and 2-chloro-2-methylbutane MR is given. Which row is correct? Percentage yield of product X and relative rate of reaction. Okay, I know that for the relative rate of reaction, since my carbon-bromine bond in 2-bromo-2-methylbutane is going to be weaker than carbon-chlorine bond. Carbon-bromine bond is weaker. I hope you all of you guys know. Carbon-bromine bond, since it has a longer bond length, it's weaker. Whereas carbon-chlorine bond, it has a shorter bond length, so it's stronger. So this one's going to be stronger, so it's going to take more time for carbon-chlorine bond to more time. So the relative rate of reaction is going to be faster for 1. So 1 is faster than 2 and 1 is faster than 2. Okay, I know this. Now percentage yield of product X. Percentage yield means that this is my actual yield. Now I have to calculate the theoretical yield, like according to theory what's going to happen. So to calculate the theoretical yield, I have to draw the product, right? So 2-bromo-2-methylbutane, first I draw this. Butane means 1, 2, 3, 4. 2-bromo means on the second bromine. 2-methyl means on the second you have a methyl group. Well, that's a tertiary halogenoalkane. And when you have tertiary halogenoalkanes, you form SN1 mechanism. You're going to follow SN1 mechanism over here. But we're not interested in the mechanisms right now. What we're only interested in, that there's a bromine here. And we have 30.18 grams of it, but we don't care. Right now, we're just going to form the product. And if we add NaOH to it, which is going to be aqueous and in excess, what's going to happen? What's going to happen is that we're going to have carbon, OH, CH3, CH3, CH2, and then CH3. Okay, so now we're going to calculate the MR of this thing, which they've given 2 bromo to 150.9, 150.9. And for this thing, where's my calculator? I'm gonna calculate. Carbon is 12 plus 12 plus 12 plus 12 plus 12 plus 16 plus how many hydrogens do we have? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 plus 12, it's 88. So from 150 grams of this, I should get 88 grams of this. Okay. Now let's make our ratio. From 150 gram of my reactants, 150.9 grams of my reactants, I should get 88 gram of this. So if I have 30.18 grams, so if I have 30.18 gram of my reactant, I should get X grams of my product. Now let's see how much product should I get in theory. 30.18 times 88 upon 150.9. 30.18 times 88 divided by 150.9, and I should get 17.6 grams of my product. Now I should get 17.6, but how much did I get? I get 12.32. Well, that's not fair. So how much is my yield? My yield is 12.32, which I got, divided by the total which I should get, which is 17.6 times 100. 12.32 upon 17.6 times 100. And that gives me a 70% yield of my reaction. Got it? A 70% percentage yield of my reaction. Where do we have 70? 70 over here. I hope you got it. Well, this was a tricky one, but not that tricky. You just had to realize, first things first, that carbon-bromine bond is going to be weaker. And the second thing is that what we expect to produce in a reaction and what we actually produce in a reaction are different things. Like, we expected that we're going to form 17.6 gram, but we actually produced 12.32 grams. That's why the percentage yield was 70%. You had to realize this thing. For that, you had to draw the products. Now the useless information over here, I'm telling you. 2-chloro-2-methyl-butane. This information was useless. Was there to trap you guys. That's all. Those who fell for this, I don't know what were they thinking about. That was to trap you. Okay. Next. Compound W contains atoms of carbon, nitrogen, and hydrogen. We're dealing with an amine or a nitrile. Okay. Acidic hydrolysis is going to produce an acid. Even if you do your alkaline hydrolysis, you're going to form a salt of that acid. Okay, so over here the functional group in W, definitely we're dealing with nitriles over here. You know, amines, they're not going to produce acid. And secondly, name of compound W. Since we're producing propanoic acid, we are adding a carbon. We're not adding a carbon to the chain. Since we're producing propanoic acid, so we should have propane nitrile, because no carbon is going to be added. You got to realize this thing. We are not adding a carbon. If we take ethane nitrile, then we're going to form ethanoic acid. We're not going to form propanoic acid because we can't add a carbon through hydrolysis. So this thing. Now we have some very beautiful diagrams of the reaction mechanisms. And a possible mechanism for the exothermic hydrolysis of 2-chloro-2-methylpropane is shown. We're shown with SN1 mechanism over here. I guess that's very clear that this is SN1 mechanism. Which diagram represents the reaction pathway diagram for this mechanism? First step is a slow step. Why is it a slow step? Because the activation energy should be high. So for the first step, we're expecting a higher activation energy. The second step is a fast step. Why is the second step a fast step? Because we're expecting a lower activation energy. See it for yourself. First step, activation energy is higher. For the second step, since reactants are here, products are here, the activation energy is lower. For the first steps, in the reactants are here, products are here, activation energy is higher. And we only have 2 steps, so we are going to have 2 peaks. When your reaction is going to proceed to 3 steps, you're going to have 3 peaks. Well, over here we only have 2 steps. Over here it's the opposite. It's shown in an opposite way. So this is not correct. The first peak should be higher because more energy is required to break the bonds first. Okay, which structure represents a part of the polymer chain of PVC, which is polyvinyl chloride? I guess it's option A. I just saw it and I just saw the two hydrogens, one chlorine, one hydrogen. Two hydrogens, one chlorine, one hydrogens, two hydrogens, one chlorine, one hydrogen. Doesn't that make sense? For over here, look, this monomer has no chlorines. Impossible. Over here, all chlorines. No. Over here, two chlorines. No. For PVC, what do you have? You have carbon, carbon. That's the monomer for PVC. Hydrogen, hydrogen. Then a chlorine, then a hydrogen, and then a double bond in between. So that's your monomer for polyvinyl chloride. And that's exactly shown in option A. Considering only structural isomers, what is the number of alcohols of each type with the formula C5H12O? Considering only structural isomers, what is the number of alcohols with the formula C5H12O? So we're going to start with, I guess, primary. Let me start with primary. I have to draw how many primary? I have to draw as many primary as I can with C5H12O. Okay, C5, 1, 2, 3, 4, 5. Well, I always get isomers wrong, but this time I'm gonna try my best not. OH here. Okay, that's pentane 1 all. Then carbon, 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 1, 2, 3, 4, 5. Just take away one carbon. Add a branch here, and that's also one pentanol, whatever. Then carbon, 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 carbon. OH, add a branch here. Okay, then carbon, 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 1, 2, 3, 4, 5. One, two, three, four, 5. So can I draw any more? Let me see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Can I draw any more? The only number of primary alcohols I could draw was 4. This is the one, this is second, this is third, and this is fourth. I'm gonna go towards the secondary alcohols. Secondary alcohols are those which have one hydrogen and one alkyl group, okay? So 1, 2, 3, 4, 5. 2 all. Then 1, 2, 3, 4, and 5. 3 all. Then okay, let me do a little branching for the second one. 1, 2, 3, 4, and then an OH here, and the fifth one here. So that's 3 I could draw for the secondary. And now tertiary, they say it's only one. Let's see. 1, 2, 3, 4, 5, and then an OH here. So that's a tertiary alcohol. Option number C. I don't know. Let's check. Yeah, it's option number C. So that was all I drew. These were the primary ones. This is, and now let me name them. This is pentane 1 all. This is 1, 2, 3 methyl pentane 1 all. This is 2 methyl pentane 1 all. Pentane butane 1 all. Let me just write the names. This is pentane 1 all. This is 3 methyl butane 1 all. This is 2 methyl butane 1 all. This is 2 dimethyl propane 1 all. Okay, so the four isomers, the primary ones were pentane 1 all, 3 methyl butane 1 all, 2 methyl butane 1 all, 2 dimethyl propane 1 all. Now we're gonna move towards the secondary. 1, 2, 3, 4. This is pentane 2 all. This was pentane 3 all, and this was 3 methyl 3-methyl butane 2-ol. Okay, this one is 3-methyl butane 2-ol. This was pentane 2-ol. This was pentane 3-ol. And the only tertiary I was able to make was only this one, which was 2-methyl butane 2-ol. That's the tertiary alcohol. Done and dusted. Easy. Structural isomerism and stereoisomerism should be considered when answering. 2,5-dibromohexane is heated and reflux with ethanolic KH. How many isomeric compounds are formed with the molecular formula C6H10? The first step over here I'll suggest is that first you see what kind of reaction is happening. What I can see is I'm going to draw everything, okay? 2,5-dibromohexane. So first I have to draw hexane, which means 1, 2, 3, 4, 5, and 6. Then I have to say 2,5-dibromo. So 2 bromine and then 1, 2, 3, 4, 5. 5 on 5 carbon I have a bromine, right? And the rest I'm just gonna fill with hydrogens. CH2, CH2, CH, and CH3. So that's my 2,5-dibromohexane is heated under reflux with ethanolic KOH. Ethanolic KOH means that you have, or you can say it's ethanolic NaOH. Don't be confused by KOH. You just think about it as NaOH. And you've studied this, that whenever you have ethanolic alkali, and you have a halogenoalkane, what happens? What kind of reaction occurs? You got to be very good with the organic reactions. You have your KOH, which is your alcoholic, or you can say ethanolic. Over here, your elimination reaction is going to occur, right? And what kind of elimination reaction is going to occur? You're going to eliminate this bromine. You're going to eliminate this bromine, and then you're going to add double bond here, wherever. Okay, so that's the type of reaction that's going to happen. Now, I personally believe that this requires a lot of working, so the space over here is not enough. So let's just copy it and do it, because there's a lot of working. And I know these kind of questions can be challenging, in which you have to work a lot. But you know, at the end of the day, they're going to pay off. So let's work. I have to start making isomers. So this is my structure basically. Now I have to start taking out things from it, like the bromines. I have to start taking them out. The first structure that I'm thinking of is that, look, elimination is going to happen on both bromines, this bromine as well as this bromine. Just don't think about it कि हम एक काम करते हैं कि हम इस जगह से निकाल देते हैं ब्रोमीन और इधर लगा रहने देते हैं. That's not possible. So अब what I'm thinking of is कि सबसे पहले हम इन यहाँ से H निकालते हैं, because this is your alpha carbon which has the bromine and this with it is your beta carbon. So सबसे पहले हम निकालते हैं this is paper 11, so I guess I gotta speak in English because majority of the audience, they might not understand Urdu. It's fine. अच्छा, so हम सबसे पहले यहाँ से निकालते हैं H, okay? इस वाले कार्बन से और इस वाले कार्बन से. ये हमारे बीटा कार्बन हैं, ठीक है? और ये हमारा अल्फ़ा कार्बन है. अल्फ़ा कार्बन वो वाला कार्बन होता है जिसके साथ हमारा हैलोजन लगा होता है. सो अब हम क्या करेंगे, हम CH2, ये मैं कोने से निकाल रही हूँ, ठीक है, इस वाले. देन इट्स CH and then we have a CH2 and then we again have a CH2, CH2 and then we have a CH double bonded CH2. Okay, that's the first kind of isomer I can think of. Now we have to consider both structural isomerism and stereoisomerism. अब इसका मतलब नहीं है कि आप अपनी मर्जी से यहाँ पे कहीं पे भी ब्रांचेस लगा दें. That's gonna be senseless. आप अपनी मर्जियाँ नहीं दे कर सकते कि यहाँ पे आप ब्रांच लगा दें. वही कर सकते हैं जो हो सकता है पॉसिबली कि एथेनॉलिक KOH में आप सिर्फ यही कर सकते हैं कि you can just add the bromine, like you can just remove the bromines and then add the double bond. तो अपनी मर्जी नहीं करनी कि structure isomerism है तो हम यहाँ पे position change कर दें functional group या कुछ और, कुछ ऐसा नहीं करना. The first thing is this. अब इसमें हमारे पास क्या कोई stereoisomers possible हैं? No. वाई नो, बिकॉज हमारा ये जो डबल बॉन्डेड कार्बन है इसके साथ 2 हाइड्रोजन्स लगे हैं, इधर और इधर, और जब हमारे पास 2 सेम ग्रुप्स होंगे तो हमें पता है कि जब हमारे पास 2 सेम ग्रुप्स होते हैं तो स्टीरियो आइसोमर हमारा नहीं बन सकता। कि हमारे पास यहाँ पे कोई सिस ट्रांस नहीं बनेगा क्योंकि सेम ग्रुप्स हैं। अब हमारे पास ऑप्टिकल आइसोमर बन सकते हैं। ऑप्टिकल आइसोमर तब बनते हैं जब हमारे पास 4 डिफरेंट ग्रुप्स एक कार्बन को सराउंड कर रहे होते हैं। तो कैन वी मेक optical isomer? No. This carbon, it's a double bond, it can't be optical, this can't be optical, this can't be optical, no optical here, no optical here. तो अभी मैंने first ये बनाया है। अब second में what I'm gonna do is I'm gonna take out HBr from here। ये तो मैं यही करूँगी, but यहाँ से instead of taking out from this beta carbon I'm gonna take it from this beta carbon। ठीक है, तो अब सेकेंड में क्या बनाऊंगी, H3C, नो CH2 डबल बॉन्डेड CH, यहाँ से ब्रोमीन निकाल दिया, अब बॉन्डेड टू CH2 बॉन्डेड टू CH डबल बॉन्डेड टू CH एंड देन CH3। समझ आई मैंने क्या किया? मैंने इंस्टेड कि मैं इधर एंड पे डबल बॉन्ड लगाती, मैंने यहाँ पे लगा दिया और इस वाले डबल बॉन्ड को इधर ही रहने दिया। ठीक है, दैट्स द सेकेंड थिंग आई डिड। अब क्या इसमें मेरे पास सिस ट्रांस पॉसिबल है? मैंने हर जगह पे रुक के, बिकॉज एग्जामिनर ने कह दिया स्टीरियो आइसोमर, तो मैंने हर जगह रुक के सोचना है कि कैन आई मेक सिस ट्रांस, कैन आई मेक ऑप्टिकल आइसोमेरिज्म और एनीथिंग। Is it possible over here? Let's see. This carbon has an H attached on top, this H, and on the other side it has this entire group. So yes, this carbon can give, and then this carbon has H attached on one side and a methyl group attached on the other side, so this carbon also give. So there is a cis possibility of this isomer and there's a trans possibility of this isomer. Done? Now, let's do one other thing. I can think of one other thing. What is that? अब मैं यहाँ से भी डबल बॉन्ड इधर करूँगी और यहाँ से इस कार्बन से जो डबल बॉन्ड आने उसको भी इधर करूँगी। सो यू नो व्हाट आर वी गोना गेट दिस टाइम? वी गोना गेट CH3 बॉन्डेड टू CH डबल बॉन्डेड टू CH, यहाँ पे एक डबल बॉन्डेड टू CH बॉन्डेड टू CH डबल बॉन्डेड, second 1 2 and then there's going to be a single bond between this and then a double bond between CH, because the Br is gone now. Okay, the Br is gone, 1 2 and then CH3. Okay, so that's what I'm going to make. और अगर नहीं समझ आ रहा तो हम इसको खोल लेते हैं ताकि फिर आसानी हो जाए। Like this, then there's a CH double bonded to CH, single bonded to CH, which is again double bonded to a CH, CH, H and H. I hope you got what I tried to do. So अब क्या इसमें cis trans possible है? Let's see. So this carbon, it has one hydrogen attached to it and one CH3. Well, it can give cis trans. And then this carbon, it has one H attached to it and this group. Well, this is a stereo center. Well, now let's look over here. If you see this carefully, you break it from here or you break it from here. This is a symmetrical alkene. Okay, symmetrical dialkene, like it has 2 alkene groups, this group and this group, and both groups can give cis trans. So the formula over here is going to be that we take the number of stereo center. This is the first stereo center, this is the second stereo center. I know it's difficult, but it's fine. So 2 raised to power n, and then we minus 1 from it. 2 raised to power 2, 2 is the number of stereo centers, 1 stereo center, 2 stereo center equals to 4, minus 1 equals to 3. So 3 isomers, stereo isomers, are going to be possible for this alkene. Okay, again telling you 3 stereo isomers for this, 2 stereo isomers for this, and no isomer for this. So in total we have 1 2 3 4 5, 6. 3 plus 2 plus 1, we have 6 isomers. I personally believe this was a difficult question. For some of you, might it have been difficult, but you just had to look at it from a different perspective, okay? And that's the solution. The first isomer, the second isomer, and the third isomer. The second isomer gives cis and trans, and the third isomer gives 3 other isomers because of 2 stereocenters. And since it's symmetrical, we use the formula 2 raised to power n, and then we subtracted 1 from it. Okay, moving on to the next question, which says, which formula represents the organic compound formed by the reaction of propanoic acid with methanol in the presence of concentrated sulfuric acid as a catalyst? Okay, so this one's an easy question. We simply have to do a esterification between ethanol and our propanoic acid. So what are we going to form? We're going to form, since we have methanol, so we're going to form methyl propanoate. And how are we going to write methyl propanoate? Well, I think this one's correct, right? This one seems correct. But still, I'm going to draw and show it to you guys. So firstly, you're going to have your propanoic acid, which is going to look something like this. I've just opened it for you guys. I know the closed formulas make you feel like bad. And then we have this is called methanol. And what happens in the presence of our sulfuric acid, which is our catalyst, these two are gonna come close together, gonna react. A water molecule, this water molecule, this water molecule is going to be eliminated. You see, I just took out a water molecule, and this is going to be joined by an ester bond here. So that's your ester, okay? And option B exactly represents this. There's a CH3, then you can see there's a CH3 here, okay? This CH3, then there's a CH2, a CH2, then COO, COO, and then a CH3, and then a CH3. Done and dusted. An organic compound J, so we have an organic compound that's named J, reacts with an excess sodium to produce organic ion with a charge of 3 negative. J reacts with an excess NaOH to produce an organic ion with a charge of 1 negative. What is the structural formula of J? Nice. So, an organic compound J reacts with an excess of sodium to produce an organic ion with a charge of 3 negative. What do you guys think? What do you guys think? What's going to be J? J needs to react. That's why I said I'm going to do the organic part first. Because you see, these type of questions, I don't think majority can solve. Personally, I don't think. When you look at J is going to be something that's going to react with sodium. And when it reacts with sodium, hydrogen gas is going to be produced. We obviously know that what kind of compounds react with sodium. Either it has an OH group, which is an alcohol functional group, or either it has a COOH group, which is a carboxylic functional group. So it should have an alcohol or a carboxylic functional group. Let's see. So over here, we need how many? When we have one carboxylic functional group, we produce an ion with a -1 charge. Over here, we need a -3 charge. So we need 3 functional groups that are going to react with sodium. Okay? Because sodium has a charge of a +1, right? It's going to balance out something that has a charge of -1. Over here, we have a -3. So we're going to require 3 sodiums. So that means we need 3 functional groups of carboxylic alcohol combined. Okay, so over here, let me count the functional group. 1 alcohol. एक सेकेंड, इसको अल्कोहल समझने की गलती तब तक ना करना जब तक आप स्ट्रक्चर नहीं बना देते, क्योंकि ये आपका एल्डिहाइड भी हो सकता है, CHO भी हो सकता है. सो लेट्स जस्ट ड्रॉ इट एंड देन सी. नहीं, ये नहीं हो सकता बिकॉज इसके साथ एक CH2 है. गुड. एंड अदर अल्कोहल एंड देन अ कार्बोक्सिलिक. गुड. O2H, carboxylic and alcohol, carboxylic, alcohol, carboxylic. Alcohol, ester, which is not going to react with sodium, and aldehyde. So now I can see I can shortlist option A and C on the basis that they have 3 functional groups, right? I need 3 functional groups. Now next thing. J reacts with excess NaOH to produce an organic ion with NaOH. What's going to react with NaOH? Tell me what's going to react with NaOH. Only carboxylic. To produce an organic ion with a charge of -1. That means J has 1 carboxylic group, right? So you can see it for yourself. A -1 means 1 carboxylic. Now we're looking for 1 carboxylic group in J. If I look at the options, you have 2 carboxylic. I only need 1 carboxylic. I'm going to explain it again. I know that's a brain teaser. -3 means we need 3 functional groups which are going to react with sodium. We have 3 functional groups here and we have 3 functional groups here. And a -1 means with NaOH only 1 carboxylic functional group can react. That means we have 1 carboxylic. In option A we have 1 carboxylic. In option C we have 2 carboxylics. Right? 28 is A. I have not checked it. Let's check it. I know I'm correct. I don't think I need to check. Yeah, I know chemistry, it's fine. But I'm just telling it to you guys, think about it rationally. Information about the carbonyl compound X is given. Compound X reacts with LiLH4 to produce a secondary alcohol, okay? So it reacts with LiLH4, that means it's being reduced to produce a secondary alcohol. We know that what kind of compounds reduced to form secondary alcohol? We know that ketones are going to react with LiAlH4 or NaBH4. These two are the reducing agents. And then they're going to form your, what do we call them? Secondary alcohols. They're going to reduce to form secondary alcohol. So we're dealing with ketones here. Compound X reacts with alkaline I2 to give a yellow precipitate. That means it has a C double bond O CHH group. Okay, that's what it's telling you about. It cannot be butanol. We're looking for a secondary alcohol. It cannot be ethanol. So let's check for butanone and pentanthrenone. So butanone is going to be 1, 2, 3, 4. Doesn't matter you put your double bond here or on this carbon, it's going to remain the same. So look over here, H, 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 and H. Firstly, it's going to react with your alkaline I2 to give you a yellow precipitate because it has C double bond O CH3 group. Well, and secondly, if we reduce it by adding LiAlH4. What's going to happen? An OH is going to add here. This double bond is going to break. And an H is going to add here. And we have butan-2-ol. We're going to produce a secondary alcohol called butan-2-ol. Right? So, option B is our answer. Now, let's check for pentan-3-on as well. Pentan-3-on means 1, 2, 3, 4, 5. 1, 2, 3, we have double bond O. Now, look at for yourself. This is going to produce pentan-3-ol alcohol. But the problem is, it is not going to react with your alkaline I2 because it does not have this group. Check it for yourself. C double bond O is bonded to a carbon that has 2 hydrogens. We need C double bond O to be, look it for yourself. We need the C double bond O to be bonded to a carbon that has 3 hydrogens to it. Over here it has 2 hydrogens. So, cross. Complete combustion of compound T produces carbon dioxide and water only. Compound T produces steamy fumes with PCl5. Complete combustion of compound T produces carbon dioxide and water only. Compound T produces, that means that it releases HCl. Compound T does not give any visible product with 2,4-dinitrophenylhydrazine, no ketone, no aldehyde. What can be reduced? Certainly from this information, complete combustion gives carbon dioxide and water only. Alcohol, if we think about an alcohol for a second, complete combustion gives carbon dioxide. Alcohol is going to give it what can be reduced with certainty from this information. It is not an aldehyde. I personally think that the last line is telling me 100% that it's not an aldehyde. So I'm gonna go with option D. Let's check. I think I'm correct. I should be correct because I've given chemistry all my life, 26 ka D. Yeah, I'm correct. Because that's the only thing I can think of. Because that certainly tells me it does not has any aldehyde. Only this is confirmatory. With PCl5, I've studied water hydrolyzes it, another thing, but I'm not sure about it, right? So I left it. Three reagents are listed: aqueous sodium carbonate, LiAlH4, and water. Which reagents react with pure ethanoic acid to give a solution containing ethanoate ions? Wow. React with pure ethanoic acid to give a solution containing ethanoate ions. Sodium carbonate is going to react because it's going to produce sodium ethanoate. LiAlH4 is not going to react. Why? Because it's going to form an alcohol instead. With water, I'm gonna tell you guys one thing that might shock you guys, that ethanoic acid reacts with water, in which it acts as a proton donor and water basically acts as a proton acceptor. So we're gonna establish an equilibrium between them. Like ethanoic acid, which is this, it basically has this H plus, right? So it's gonna react with water and it's gonna form CH3COO, which is the ethanoate ion, plus H3O positive, because water is going to be a proton acceptor over here. So this is your proton acceptor and this one is your proton donor. So that's an acid base reaction, which ethanoic acid reacts as an acid and water reacts as a base because it's accepting this proton from it, and then we form an ethanoate ion. So this is also going to react with water. 1 and 3. I know we haven't started this. I know it's not part of the course, but well, they're going to test you things that are not part of the course. This just shows this, that you're going to be tested for a lot of things. Okay. Compound X contain two period 3 elements, Y and Z. Compound X reacts with water. Okay, so it contains two period 3 elements to form two products: a slightly soluble hydroxide, and compound Q. So maybe it's an oxide, like magnesium oxide, which might form magnesium hydroxide. I think I'm just thinking about it, like I'm not sure, but over here I can see in the options that we cannot have sodium because sodium hydroxide is going to be like highly soluble. So magnesium hydroxide, maybe. And compound Q, what's Q? I don't know. Q is a compound of an element Z and hydrogen. So element Z and hydrogen. Okay, so element Z and hydrogen. Okay, sulfur and hydrogen. Element Z, sulfur and hydrogen. pH4, SH something. Okay, let's see. Compound Q. Q is a compound of element Z. It contains element Z like phosphorus or sulfur and hydrogen. I guess it's going to be pH4 phosphine or something. Compound Q burns in moist air to produce oxide and water. Okay, this might burn this or this, which contains sulfur and hydrogen, phosphorus, hydrogen. In moist air, air contains oxygen to form an oxide, P4O10, and water. I have to do this. You know why I have to do this? I'm just doing it randomly. Why? Because if I don't do it, I'm going to lose track. So SO2 plus water. Let's see what happens. The oxidation number of element Z in the oxide is +5. This is the oxide. Look, over here, the oxidation number of phosphorus is +5. And for oxygen, it's a -2. Check it for yourself. -2 for oxygen, P4O10, yeah? And +5 for P4O10, yeah? Whatever, I just know that my phosphorus has a oxidation number of +5. Okay, so I'm going to consider it to be phosphorus. Is it phosphorus? 24. Yeah, it is phosphorus. It is phosphorus. I told you only phosphorus can lose 5 electrons. Nah? Sulfur cannot lose 5 electrons. It can, but it doesn't. Phosphorus basically loses 5 electrons. So that's the thing I just considered over here. +5 told me that it's going to be some phosphorus oxide. Okay, we again have a group 2 question, I guess. each mineral listed behaves as a mixture of two carbonate compounds. They can be used as fire retardants because they decompose in heat, producing carbon dioxide. The gas smothers the fire. Baryotosite, dolomite, huntite. What is the order of the effectiveness as the fire retardants? Retardants, whatever. Each mineral behaves as a mixture of carbonate compound. They can be used as fire because they decompose in heat, producing carbon dioxide. The more you decompose, the more better fire retardant you're gonna be. So barium is the worst decomposer, right? Because you know that magnesium, calcium, strontium, barium, radium. Okay, that's group 2. And in group 2, as you go down the group, what happens? That your thermal stability decreases. Your thermal stability is going to decrease. So this is going to be least thermally stable, and this has 3 magnesium. So this is going to be most thermally stable. So huntite is going to be the best, and baryotosite is going to be the worst. That is according to my logic, because it has a barium thing in it and it has 3 magnesium. Magnesium is going to be least thermally stable. It is 1 magnesium, so like less better than huntite. So huntite is going to be the best because it's going to decompose more readily. The table shows the data for elements in period 3. We're given with the melting points, we're given with electrical conductivities. God knows what they're going to ask. Which statement is correct? All the elements in the table with a giant structure have higher melting point than each of the elements in the table with a simple molecular structure. Okay, let's see. Let's see how many giant we have. Giant, metallic. Silicon is going to be giant covalent. And then this simple, I'm going to highlight with purple. Simple, and simple, right? This is not even simple molecular, it's just like not molecules in argon. So over here we can see that sulfur has a higher melting point than sodium. Despite being a simple structure, it has a higher than sodium. Sodium is a giant structure, which makes my option 1 incorrect. Not all giant structures have higher. Next, magnesium has a higher melting point than sodium. Magnesium has a higher melting point than sodium because it has more delocalized electrons and stronger electrostatic attraction between the delocalized electrons and the metal lines. 100% correct. Because magnesium is going to have 2 delocalized electrons and sodium is going to have 1 delocalized electron. So that's correct. Phosphorus and sulfur do not conduct electricity because they're simple molecular solids at room temperature. Yes, they don't conduct because they're simple molecular, and better reason would be because they don't have any delocalized electrons. So 2 and 3 makes sense, right? 1 is wrong. Why is 1 wrong? You guys got to know. We just looked at the table and the table told us. Radium is an element below barium and grouped of the periodic table. Which equation shows what happens to solid radium nitrate when it's heated strongly? Simple. Equation. I'm just cutting out the equations I know are not correct. We've learned this equation. Simple. It's learning to balance the equations. You take 2 radium nitrates, you form 2 radium oxide, you form 4 nitrogen oxide and 1 oxygen. If you just half it, like take 1 radium nitrate, you're going to form 1 radium oxide, 1 nitrogen dioxide and half moles of oxygen. That is what we have learned. The diagram shows the electronegativity of 3 elements, sodium, magnesium, aluminum, silicon, plotted against the first ionization energies. So what's going to be most electronegative? Obviously silicon, because across the period it increases. So cut this. Silicon should be at the top. Over here silicon is at the top. And now we have to plot the first ionization energy. Across the period it increases. So silicon should have the greatest. And then between magnesium and aluminum, though theoretically aluminum should have more, I'm saying that aluminum should have more, but we know that there's a dip in the ionization energy chart. If you guys remember the ionization energy chart, it increases and then there was a dip, then it increases, then a dip and then increases. So the dip was between group 2 and 3. So that's why aluminum has lesser ionization energy than magnesium. Magnesium is going to have more. That's why option B. Which reagent or reagents and conditions with oxidize chlorine into a compound containing chlorine with a +5 hot concentrated NaOH? No explanation needed. We've done this reaction. When we make it react with hot concentrated NaOH, what do we form? We form NaClO3, which has a chlorine with +5. And when we make it with cold dilute NaOH, we form NaClO, in which chlorine is just a +1. So that's the difference. And then you balance equations. You form NaCl in both. You form water in both. We've done it. That's easy. 3 statements about halogens: chlorine, bromine, and iodine and their compounds are listed. The halogen with the highest boiling point has atoms which form the strongest bond to hydrogen. Highest boiling point is of iodine, but it forms the weakest bond with hydrogen. The highest boiling point is going to have the most number of electrons, because over here we have induced dipoles, temporary dipoles that depend on the electron number. Halogen with the strongest instantaneous dipole forms the most thermally stable hydrogen halide. Yeah, no, that's completely, I don't want to say that word, but that's completely dash. Why? Because iodine has the strongest instantaneous dipole and it forms the weakest bond with hydrogen. Cross, the most volatile element most rapidly oxidizes hydrogen. Yeah, oxidize means takes away electron. Yeah, the most reactive is going to be chlorine, and chlorine is the best oxidizing agent. Not better than fluorine, but in these 3, chlorine is going to be the best, so it's going to oxidize hydrogen. So 3 only. Okay. Which reduction process occurs on the surface of a catalytic converter? Reduction of carbon monoxide? No, oxidation of carbon monoxide. Reduction of nitrogen oxides? Yeah, we reduce nitrogen oxides to form that thing, nitrogen gas. From nitrogen oxides, we form nitrogen gas, and that is a reduction because we take away its oxygen and form nitrogen gas only. Okay. A reaction involving ammonium ions is shown. We have ammonium ions, that's a Bronsted-Lowry acid base. Ammonium is a proton donor, OH is a proton acceptor, and in the reverse reaction, that's going to be conjugate acid base pair they are. In the reverse reaction, ammonia is a base. In the forward reaction, ammonium is an acid, and in the reverse, this is a base. Okay, leave. The ammonium ions are reduced. They're reduced. There's no change in oxidation number. I don't think there is. In the reverse reaction, ammonia acts as a Bronsted-Lowry base. Yeah. In the reverse, ammonia is a base because it's accepting a proton to form ammonium. The ammonium ion and ammonium molecule have the same bond angle. Not at all. Ammonium ion is 109.5. Tetrahedral ammonia has a trigonal pyramidal. It's a pyramid shape. The reaction is not a redox. Yeah, it's not a redox. Nothing is changing. It's an acid base. Reaction 2 and 4. In which pair do both species have the same shape, have the same number of covalent bonds, have the same shape? Water and oxygen. Okay, boron trifluoride and ammonia, carbon dioxide and nitrogen, methane and ammonium ion. The same shape, have the same number of covalent bonds. A, methane ammonium ion. So over here, I guess it's easy that oxygen is going to be just like O double bonded to an O, and there's going to be a single bond here. So the bond angle, the bond is going to repel, and they're going to be like a maximum angle. Well, that simple. Boron trifluoride is going to be trigonal planar, ammonia is going to be pyramidal, carbon dioxide is going to be linear, whereas nitrogen, it has lone pairs like nitrogen, then triple bonded to nitrogen, and then there's a lone pair here, there's a lone pair here, so the lone pairs are going to repel the bonding pairs. So there's going to be some kind of angle. It's going to be like this shape, but carbon dioxide is going to be like flat because there are no lone pairs on the carbon atom, and then methane and ammonium, they're going to have proper bond angles. Which statement about the 3p orbital is correct? We're not talking about the 3p subshell, we're talking about the 3p orbital. Okay, it can hold a maximum of 6 electrons. No, it can hold 2 electrons, right? Look, two electrons one orbital can hold. That is what I think. It has the highest energy of the orbitals with the principal quantum number 3. No, the highest energy is going to be 3d, not 3p. It has the higher, it is at a higher energy level than the 3s orbital. Yeah, it is at a higher energy level, but has the same shape. No, 3p is going to be like this and 3s is going to be like this. That is the shape for the s orbital, and this one is the shape for the p orbital. It is occupied, obviously, when this is crossed, this is crossed, this is crossed. This has to be correct. Let's see what is this. It is occupied by one electron in an isolated phosphorus atom. Let's draw the electronic configuration for a phosphorus atom. It says 1s1. Phosphorus is 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 10 electrons done. 3s2. In an isolated phosphorus atom, we have to fill 15 in a phosphorus atom. So that's 10, 11, 12, 13, 14, 15. Just it is occupied by one electron in an isolated phosphorus atom. Look, this is the 3p orbital, just occupied by one electron. This is a 3p orbital occupied by one electron. So there are three 3p orbitals all occupied by just one electron. You can see it for yourself. 2p6, 3s2, and then this is 3p3. Okay, so that's the thing over here. Now we have an interesting question which says the diagram shows two containers of methane connected by a closed tap. So we have methane here, we have methane here, we have a closed tap here. Each container has a volume of 1 meter cube. So what you're going to say is this entire volume, this volume is going to be 1 meter cube, and this volume is also going to be 1 meter cube. Okay, the tap is open, the temperature of the system is changed to 800 Kelvin. The system reaches a constant pressure. What is the pressure of the methane within the system? Okay, so now we are gonna see that we have a total of 2 dm cube volume, 1 dm cube here and 1 dm cube here, and over here we have 16 grams of methane at 100 kilopascals, and over here we have 96 grams of methane at 200 kilopascal. These kind of questions are very common, and you got to learn a method to solve them. The formula is going to be very simple. It's going to be PV equals to nRT. For that, we know the volume. It's going to be not dm cube, sorry, it's meter cube. Sorry for this. It's going to be 2 meter cube. I need to figure out the total moles of my methane. I know the R, I need the T. T is going to be 800 Kelvin, and then I'm going to figure out the pressure. So first I'm going to figure out the amount of moles that are going to be present in 16 grams of methane. I know the formula for moles. Moles equals to my mass upon MR. Mass is 16 divided by MR, which is also 16. How many moles do I have? I guess that's going to give me 1 mole, right? And then 96 divided by 16. 96 divided by 16, I get 6 moles. So I have a total of 6 plus 1, 7 moles of methane that are going to be mixed together, right? So P equals to 7 moles times R, which is 8.31, times 800, which is going to be my pressure, divided by my V. V is going to be 2. So let's see how much do I get. 7 times 8.31 times 800 upon 2. That gives me a volume pressure of 23268, and converting it into kilopascals, I'm going to divide it by 1000, and then I'm going to get 23.268 kilopascals, which matches my option number A. So that's how you do. Question number 12 states that barium dithionate BaS2O6.2H2 is soluble in water. Okay, so it's going to dissolve in water. H2O6 2 negative ions decompose slowly in acidic solution. So what's happening is that these ions, these are decomposing to form SO2 and sulfate ions. Now we have sulfate ions and we have some barium thing, okay? I think it should just click in your mind that when these are going to decompose, when this part is going to decompose, the sulfate part is going to react with the barium to form barium sulfate. Okay, next part states that 3.513 gram of BaS2O6.2H2O is dissolved in 100 cm cube of volumetric flask in a solution made up to the mark with HCl at time x minutes, a white precipitate of mass 0.661 gram is present in the flask. What is the concentration of BaS2O6 in the volumetric flask? Okay, so first we got to realize the initial moles. I know this might seem a little tricky, a little brain teaser question, but you just have to find the moles of this BaS2O6.2H2O. Let's find them. So the moles are going to be 3.513, which is the mass upon the MR. For that, we need the MR for barium. It's 137.3. So for barium, it's 137. First, we have 3.513 on the top, 137.3. For sulfur, it's 32 plus 32 plus 32. For oxygen, 16. 16 times 6 plus 2 times 18. And how many moles do we get? I've just written 137.3 plus 32 times 2 plus 16 times 6 plus 2 times 18. So that's the MR of this entire compound. And we get 0.01054 moles. Okay, we have the initial moles. We have to find the change in concentration. So we need to find the change in moles at x minutes, right? At x minutes, the white precipitate of mass, this is present in the flask. The white precipitate is going to be of BaSO4, barium sulfate. That's going to be the white precipitate. So now we find out the moles of the white precipitate. That's going to be mass, which is 0.661 upon MR. MR of barium sulfate is going to be 137.3 plus 32 plus 16 times 4. And let's see how many moles do we get of barium sulfate. 0.661 upon 137.3 plus 32 plus 16 times 4. And that gives me how many moles? BaSO4. I get 0.002833261 moles. Now I have the moles that are formed. Okay, so the change in concentration is gonna be my initial moles minus my final moles is dissolved in water in 100 cm cube. Okay, so I have to find the concentration of BaS2O6 in the volumetric flask, the concentration. Okay, I don't have to find the change, I have to find the concentration at time x minutes. So these many moles have been decomposed, and these were the initial moles. So this minus this is going to give me the amount of moles that are present, and then I divide the moles by volume, I get the concentration. So my initial moles were 0.01054, and at x minute these many were decomposed. Why these many were decomposed? Because this much BaSO4 was formed. Because over here we see if 1 mole of SO4 is formed, 1 mole of S2O6 2 negative is decomposed. So we know that 0.002833261 moles have been decomposed. We say 0.01054, and we get how many moles that are present? We get 0.007706738 moles. Now these are my moles that I'm getting. Moles divided by the volume, which is 0.1. Why 0.1 volume am I taking? Because I have 100 cm cube, and if I convert it into dm cube, I get 0.1 dm cube. Okay, so my answer divided by 0.1 gives me 0.077 mole per dm cube. 0.077 mole per dm cube. I hope you understood. This was a little tricky question. You just had to realize that you needed the amount of moles of this at x minutes. So you just took out the initial moles, then subtracted the moles that were decomposed from it, and you got the moles that were remaining, and then you divided the moles by volume and you got the concentration. So the next question states that 50 cm cube or 1 mole per dm cube. So we have the moles, we have the volume, we have the concentration. We can easily calculate out the moles of H2SO4 is added to 100 cm cube of, again, we are given with the moles, 1 mole per dm cube NaOH in an insulated vessel. Both the solutions are at the temperature of 20 degrees Celsius before mixing. After mixing, the temperature rises and the highest temperature reached is 29 degrees Celsius. Okay, so let's write the equation between sulfuric acid, H2SO4, and NaOH. What are we going to form? We're going to form sodium sulfate, which is going to be Na2SO4 plus water, right? And we're going to get 2 moles of this, and we're going to get 2 moles of water. That's a proper balanced equation. From this, we can easily figure out that 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. No worries. Assume that all the energy released, all the energy that is coming out in the reaction goes into raising the temperature of the aqueous reaction mixture. We're assuming no energy is lost. So this 9-degree rise that came over here is because of this exothermic reaction. The specific heat capacity for the mixture is 4 joules per cm cube per Kelvin. What is the value of the enthalpy change of neutralization determined from this experiment? Okay, so first, what you're gonna do, we're gonna figure out the moles of sulfuric acid and we're gonna figure out the moles of NaOH. For sulfuric acid, we have, for the moles of sulfuric acid, we just multiplied the volume, which is 50, times the concentration, which is 1, divided by a 1000. Why do we divide it by 1000? You should know that we always need it in dm cube, not in cm cube. So 50 times 1 divided by 1000, that's simply 50 divided by 1000, and what do I get? I get 0.05 moles. And for my NaOH, how many moles do I get? I get 100 divided by 1000, that's 100 into 1 divided by 1000. I get 0.1 moles. Now you can see that they're gonna exactly react. No one is the limiting reactant because 1 mole of this reacts with 2 moles of this. So 0.05 moles of this are exactly gonna react with 0.1 mole of this. So both are gonna be entirely used up. Okay. What is the value of the enthalpy change of neutralization determined in this experiment? वैसे तो if I just don't perform it, I know by I don't calculate it out. I know for neutralization it's always like 57.7 or something like this. So for that it makes sense that it's option B, but still let's just calculate. Q equals to, what is the enthalpy determined from this experiment? MC delta T. The mass of the solution is going to be 100 plus 50, which is 150. C they've given is 4.2 times the rise in temperature is 9 degrees. You can take the rise in degrees. And this is going to be divided by the moles of the limiting reactant. Since over here, I can find that both of them have equal moles. No one is the limiting reactant. Both of them can be entirely used up. So I'm going to take the moles of sulfuric acid then, I think. So 150 into 4.2 into 9, that gives me 5670, and if I divide it by 0.05, I get a lot of moles. And if I divide it by 5670, 5670 divided by 0.1, I get 56700. So I am dividing it by the moles of my NaOH. एक second, 0. Oh my gosh, just realized something. 0.1 times 2, 0.05 times 2, that gives me 0.1. So that means in this case, when no one is the limiting reactant, we divide by the moles that are more in number. We divide by the highest moles. So over here we're dividing by NaOH moles, not by sulfuric acid moles, okay? We usually divide by the moles of the limiting reactant, but over here we're going to divide by the moles of NaOH. Why? Because enthalpy change of neutralization is when 1 mole of water is being formed. You can see over here we're forming 2 moles of water, right? So what are we going to do? We're going to divide this heat change. This is going to be for 2 moles of water. We need for 1 mole of water, right? I know this can be tricky, this can be challenging. That's why we wrote the equation. So we're going to divide this by not this by 2, you're going to divide this by the moles of this by 0.1, not by 0.05. So it's going to be divided by 0.1 by the moles of the thing that has the same moles as the moles of water, because we want, when we're considering when 1 mole of NaOH is going to react, then how much heat is going to be released. So that's why we're dividing by 0.1 by the moles of NaOH, because when 1 mole of NaOH is going to react in half mole of sulfuric acid, then 1 mole of water is going to be formed. So when we divide it, we get this, and when we divide this answer by 1000, we get this, which is negative 56.7 kilojoules per mole. Okay, well, that was tricky. You had to realize, if someone doesn't know that enthalpy change of neutralization means 1 mole of water, he could have never figured out that there are 2 moles of water being formed. If someone doesn't know how to write equations, how could that person figure this damn thing out? Okay, dinitrogen tetroxide N2O4 decomposes reversibly. Okay, this forming this, and you release 58 kilojoules per mole energy. An equilibrium mixture of N2O4 and NO2 gases is placed in a closed container under standard condition. The Kc value is given. The conditions are changed. Under the new conditions, the Kc is this. What change occurs? Okay, so there's a very important line. You should never forget it in chemistry, which says that only temperature can change your equilibrium constant, or Kc or Kp. Only temperature, no catalyst, no pressure, nothing can change it except temperature. So the temperature increases or decreases. We have to figure it out. Okay, so cross, only temperature can. We can see what happens to the Kc value. Does it increase or decrease? It's going from a -1 over here to a +3, right? So the Kc value is increasing, if I'm not wrong, right? The Kc value is increasing. When the Kc increases, that means your product is increasing, because Kc value is directly proportional to the amount of your product. Because what's the expression for Kc? Kc equals to the concentration of your products divided by the concentration of your reactants. So in the Kc equation, the products are on the top, right? So this quantity and this quantity have a direct relation, and this quantity and this quantity have an inverse relation, right? So Kc is going to increase when the products is going to increase. That means your NO2 is increasing. And how can NO2 increase in a endothermic reaction? Obviously, if you increase the temperature, the reaction is going to move forward. Increasing the temperature is going to move the reaction forward. And when the reaction is going to move forward, it's going to make more product. Why? Because it's an endothermic reaction. When you increase the temperature, the reaction mixture tries to decrease it. And in order to decrease it, it moves forward, right? So you are increasing the temperature. You increase the temperature, reaction mixture tries to decrease it, hence it moves forward, the amount of your product increases, and the Kc value also increases. Okay, so that's what's happening over here. An aqueous solution X contains substance HQ, which behaves as a weak acid. Weak acid means it's going to donate a proton. You can see over here, a proton is coming out of it, and then a Q negative is coming out of it. The soluble salt NaQ is added to X. So what are you going to add? You're going to add more Q negative ions, because NaQ is soluble salt, right? So it's going to form Na positive ions, which are going to be aqueous, and it's going to form Q negative ions. Now you can see over here, this is an equilibrium. So if you're increasing this fella right here, you're increasing the Q negative, what's going to happen? What happens to the H plus in the pH? You're increasing this part. You're increasing this part. You're increasing the Q negative, because dissolving this salt means increasing this. So if you increase this, equilibrium is going to move towards HQ side. Why HQ side? Because it wants to decrease this fella. And when it's going to move backward, what's going to happen? H plus is going to decrease, and when H plus decreases, the pH increases. I don't think that needs any explanation. When your hydrogen ions are going to decrease, the more the hydrogen ions, the more negative the pH. And the less number of hydrogen ions, the more positive the pH. So the pH is going to increase. And if the hydrogen ion decreases, the pH never decreases, it increases, right? And if the hydrogen ion increase, the pH can never decrease, it increases. So only this option and this option could be considered, B and D. But out of them, B makes sense because you're increasing Q negative. Well, next question, which diagram represents the lattice structure of sodium chloride? Okay, the lattice structure of sodium chloride. So why would, in a sodium chloride, why there would be chlorine atoms and sodium atoms? We don't deal with atoms, so straight away cross wherever I can see atoms. Secondly, we're dealing with a lattice structure. Lattice means there's going to be a regular arrangement. This seems like a very irregular arrangement. Secondly, over here, now we have to look at the size. You know that a sodium ion, how many electrons a sodium ion has? Well, it has 2 shells. A sodium ion has 2 shells, and in those 2 shells, how many electrons do we have in total? If you guys remember, how many electrons? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. We have a total of 10 electrons, and there was previously a last shell which sodium just lost, right? Because initially it had 11, so it's 2, 8, the electronic configuration for sodium. Now the electronic configuration for chlorine, configurations are very important over here. Now if I draw chlorine right here, you're gonna see it for yourself that a chlorine atom is larger than a chlorine ion is larger than a sodium ion, because so we basically have 8 more electrons in a chlorine atom, and one is going to be gained from a sodium. So this one's a sodium's electron. So 2, 8, 8. So a chlorine ion is definitely larger in size than a sodium ion. So we're looking for a negative ion that's larger. Over here, the positive ion is larger. That's incorrect. The chloride ion has to be larger than the sodium ion. So option number B. Right? Okay, substance W has the physical properties shown. The melting point is this, the boiling point is this. Of solid, electrical conductivity poor, of liquid good, and insoluble. Is it aluminum oxide? Is there any option of aluminum oxide? I just looked at it and I knew it's going to be aluminum oxide. Why? Because only aluminum oxide is an ionic compound that's insoluble in water, right? And of liquid, definitely it's going to be good because it's an ionic compound. And solid, it's going to be poor. Why it's going to be poor? Because it's an ionic compound and ions are unable to move. Next question. P is a compound that burns in an excess of oxygen to give carbon dioxide and water only. So we're dealing with a hydrocarbon here. Okay, 2.2 grams of P contains 1.2 gram of carbon and 0.2 gram of hydrogen. Okay, so that's a very interesting question. When P is added to sodium carbonate, bubbles of a gas are seen. So we cut this aldehyde. Aldehyde are not going to react with sodium carbonate. We deal with this sodium carbonate. So over here you can see a this group. What is this? This is alcohol. Not gonna give bubbles. So we consider this and this. Now what's the thing? We say that let's calculate the MR of this thing. For CH3COOH for ethanoic acid, what's gonna be the MR? It's simply gonna be 12 plus 12 plus 16 plus 16 plus 3 plus 1, right? 60. It's going to be 60. I think it's going to be 60. So if we have 60 grams of our ethanoic acid, how many grams of carbon does it contain? It is going to contain 12 plus 12 gram of carbon. That's 24. So if we have 2.2 gram of P, we have 2.2 gram of this. How many grams of carbon is it going to contain? X equals to 24 times 2.2 divided by 60. It is going to contain 0.88 grams of carbon. Definitely not this, because this thing contains 1.2 grams. So that's incorrect. So we're gonna go with option D. I didn't even have to do anything. I just proved that option B was wrong. But still, for you guys, I'm gonna prove that option D is correct. How do I prove it? I know it's 1, 2, 3, 4. It's butanoic acid. So first I'm gonna calculate CH3, CH2, CH2, COH. First I'm going to calculate the MR for butanoic acid. That's going to be 12 times 4 plus 8 plus 16 plus 16, and that's 88. So 88 grams of butanoic acid is going to give me 48 grams of carbon, right? Because the total mass of carbon is this. So if I have 2.2 gram of butanoic acid, it's going to give me X grams of carbon, and X comes out to be 48 times 2.2 divided by 88, and that exactly gives me 1.2 grams, which is this. You can check it for yourself. So first we shortlisted the acids, and then we just worked out with some simple moles. Not a difficult thing at all. The reaction of hydrogen with oxygen is shown. Okay, the reaction of hydrogen with oxygen is shown. We have hydrogen, we have oxygen, we're forming water. Which expression corresponds to the standard enthalpy change for this reaction? Okay. Okay. So combustion of hydrogen. Yeah, combustion of hydrogen, but 2 moles combustion of hydrogen. So 2 moles formation of water. Is it formation of water? Yeah. Option number A. 2 moles formation of water. That's correct. Formation is when 1 mole of a compound is formed from its elements. Over here, 2 mole of a compound is formed. So 2 times formation. I don't even have to check this thing. Leave it. Okay, the first 7 ionization energies of an element between lithium and neon in the periodic table are shown for between lithium and neon. So let's check where is the big jump from. Look, from 13,000 to 71. That's a very big jump. This entire small jump, but over here, big jump. So the first 7, so first, second, third, fourth, fifth, sixth, seventh. So from 6 to 7, there's a big jump. That means this element has 6 electrons in its last shell. And if it has 6 electrons in its last shell, that means it is in group number 6. And if it's in group number 6, and they said it's between lithium and neon, it's going to be oxygen. Okay, and if it's going to be oxygen, the electronic configuration of its last shell is going to be 2p1234. 2p4. Where are we? 2s2, 2p4. Easy peasy lemon squeeze. I don't think even that needs explanation. That's so easy. Okay, in the diagram, curve X was obtained by measuring the volume of oxygen produced during the decomposition of 100 cm cube of 0.1 mole per dm cube of hydrogen peroxide. Curve X was obtained like this. A catalyst manganese oxide was used. Which alteration to the original experimental conditions would produce curve Y? Okay. So now for curve Y, first things first, the rate is slower. Okay, the gradient for curve X is steeper, the gradient for curve Y is smaller. So adding more manganese oxide, definitely, if you add more catalyst, how can the rate be slower? Raising the temperature, if you raise the temperature, how can the decomposition be slower? Like, so adding some 0.1 mole dm cube of hydrogen peroxide, or either it's adding water. Now we can see one thing, that the amount of the product is also increasing. So that means definitely we added more hydrogen peroxide. That makes sense because the product is also increasing. The rate is getting slower. Yeah, I get it. The rate's slower. But the problem is that the product is increasing, and the product cannot increase if you add water. We gotta have more of the reactant, and the reactant is hydrogen peroxide. Only that is how the product can increase. Okay. The rate of the reaction between a reactive metal and an excessive dilute acid is investigated. The total volume of hydrogen gas produced every 30 seconds for 3 minutes is known. Okay, the average rate of the reaction during the first 30 seconds is P. The average rate of the reaction during the last 30 seconds is Q. What is the value of P minus Q? Okay, the average rate of the reaction, so it's given in centimeter cube per second. Rate of the reaction is the change in the concentration, which is in the first 30 seconds, which is 0 minus 64, which is 64 divided by 30. 30 is the seconds that we're dealing with. So 64 divided by 30 is going to give me the rate for the first 30 seconds. The rate is 2.133 centimeter cube per second. Okay, for the last 30 seconds, you can see what's the difference. 161 minus 167, that's 6. 6 divided by 30. So 6 divided by 30, it gives me 0.2. Now 0.2 minus 2.133, that gives me 1.933. Option number B. Easy? I know it's easy. Isocyl reacts with water in a redox reaction. What are the numbers V, X, and Z in the correctly balanced equation? Okay, so what's happening over here is that we got to balance out the redox things. Okay, over here we can see that ICl3 is a positive 3. Okay, and chlorine is a negative 1. Okay, and then water, I don't know. Then over here I can see chlorine as a negative 1. Over here I can see iodine as a negative 1. Over here I can see iodine as a positive 5. Over here chlorine is a positive 5. Okay, so what's happening is that a lot of redox thing is happening. Chlorine is going from a negative 1 to a positive 5. Okay, so how many electrons in total is chlorine losing or gaining? A total of 6 electrons, I think, are being lost. 6 electrons lost. 6 electrons are gone. Doom. Okay. So there are 3 chlorines, and over here we have 2 chlorines. 1 chlorine is doing nothing, like the oxidation number stays the same, but 1 chlorine is losing 6 electrons. Okay, now let's see how many more electrons are gained and lost. Now if you look at I, what's happening to I? Over here, I is losing or gaining? Gaining how many electrons? Gaining 3, positive 3, gaining 4 electrons. So we are over here gaining 4 electrons. And then over here, what's happening to what? Not over here, just a little bit if I move it here. Yeah. Over here, what's happening to I? I is gaining 4 electrons over here, and then I is losing how many electrons? Losing 2 electrons. Okay, losing 2 electrons. Now total electrons lost are 6, 7, 8, and total electrons gained are 4. Okay, first things first, we got to make the gain and loss of electrons equal. How do we make the gain and loss equal? Nobody's at all. What are you gonna do? Okay, just think about it for 2 seconds and you're gonna get it. What are we gonna do to make the gain and loss equal? So I can see there are 2 and 3 over here. So I am 16 electrons lost and 2 electrons lost. If I add a total of 2 here, now what happens? Now I'm gaining 4 electrons and gaining 8 electrons and losing 4 electrons. So there are a total of 4 electrons. No, I need 6 electrons because over here this also has to lose. So this also has to lose. So if it's losing 6 and this is losing 2, 6, 7, 8, and if I add a 2 here, then I'm good to go. Good. देखो ये 6 लॉस्ट हुए, यहाँ पे 2 लॉस्ट हुए, 6, 7, 8 हो गए. अगर मैं गेन भी 8 कर लूँ यहाँ पे 2 लगा के, I am good. And if I add a 2 here, then I have to add a 2 here because that's how it's balanced. And now are my chlorines balanced? I have 3 chlorines here. So, and I add a 2 here. Okay, and then what do? I balance my oxygens and hydrogens. Now my gain and lost is equal. Okay, now how do I balance my oxygens? I have 3 plus 3, 6 oxygens on this side, and so I add a 6 here. Okay, 3 plus 3, 6, and I add a 6 here, and then I have 12 hydrogens. So that's 1, 2, 3, 4, 5, 6. I have 12 hydrogens. I have to balance this stuff. How do I balance the hydrogens? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 6 over here, 12 over here. I need to double the hydrogens here. If I add a 2 here, that means that now my 12 electrons, there are 3 chlorines, okay? And out of those 3 chlorines, 2 chlorines do nothing, okay? I'm saying that my 2 chlorines are doing nothing. But my 1 chlorine loses 6 electrons. If I say that my 2 chlorines are gonna lose 6 electrons, that means a total loss of 12 electrons. And 12, 13, 14, Z is gonna be 1. So I don't need to change this. This is gonna be 1. Thanks for helping. This is gonna be 1. Now I just need to balance my X. Okay, X can either be 8 or 5. X can either be 8 or 5. If I put a 8 here, it's not gonna matter at all. You know why? Is it not gonna matter? Yeah, I got it. Look, if I put a 8 here, 8, 9, 10, I need 12. 9, 10, 11, 12. Done. I'm done with it. Yay, who? 8 over here and 2 over here. Is it option number A? No, it's option number C. It's not a 2, it's a 3 here. Why a 3 here? Let me check. What are the numbers? For this, it's not a 2. I need to balance this. Because when I add a 8 here, my chlorines get unbalanced. That's the thing, I'm sorry. Chlorines are going to be a total of 8, 9 over here. And now I need 9 chlorines on this side. So, that's the thing. And 3 times is going to make it 9. And now I have 9 chlorines. Yeah, sorry, I forgot the chlorines. I have 9 chlorines on this side. And now the total electrons that are being lost and gained are still going to be the same. Why? Because 2 of my chlorines are doing nothing. Only 1 chlorine is doing. And 3 iodines, they're going to just, when it's going to add up the gain and loss, it's going to become equal. So that's why option number C, to balance out the chlorines. And that's all.